Good morning, class. This is Mr. Eggleston, and this is lesson 7.1 for Algebra 1, Quadratic Growth. We pretty much exhausted everything to do with linear. And now we are moving on to quadratic. And we're going to understand the learning targets are that we're going to understand that the quadratic functions have a linear rate of change. We'll talk about what that means. Or a constant second difference over equal time intervals of the domain. Okay? Linear rate of change. A rate of change. We've seen that with the linear being that as you go from one point to the next, you add 3 each time. So we would say that the rate of change was plus 3. Here, you're going to find out that as you go from one term to the next, you're going to add a number that's not constant, but that the number you're adding grows linearly, which is kind of a weird thing. We're going to see what that looks like. We're going to identify patterns or scenarios that can be represented by quadratic functions, and we're going to distinguish quadratic growth from linear and or exponential growth. Okay, so moving on, here's our activity. We have a array of starbursts. I'm not a big starburst fan. I've never liked them that much, but I know a lot of kids like them. The first figure has, so for figure 1, there's 3 starbursts. For figure 2, 3 rows, I should say. For figure 2, there's 1, 2, 3, 4 rows and 2 columns. For figure 3, there are 1, 2, 3, 4, 5 rows and 3 columns. So the number of columns seems to equal n if n is the figure number. And then if you look at the number of rows, it appears to be 2 more than the number of columns. Figure 4, there are 4 columns. And 1, 2, 3, 4, 5, 6 rows. Describe what is changing. Okay, what is changing? Well, the number of columns and rows are increasing. Okay, the rectangle itself, if this is a rectangle, right? If this is a rectangle, the rectangle is growing. The rectangle is growing, and the number of starbursts. # number, the number of starbursts is increasing. Okay. What would figure 5 look like? Well, figure 5 would have five columns and 7 rows of starbursts. And it says, can you determine? Yes. It would be, well, if you notice, the number of starbursts, like here in figure 2, it's 2, 4, 6, 8. So there's 8 here. There's 15 here, and there's 24 here. Notice it's just 6 times 4 to get 24, 3 times 5 to get 15. So 5 times 7 would equal 35 starbursts. Okay, figure number 1, number of starbursts. Well, it is 1 times 3, which equals 3. For figure 2, it's 2 times 4, which equals 8. For figure 3, it's 3 times 5, which equals 15. For figure 4, it's going to be 4 times 6, which is 24. For figure 5, it'll be 5 times 7, which is 35. And if you look at this, it's always 1 times 2 more than 1, right? So 1 times 3, 2 times 4, 5 times 7. This would be 10 times 12, which is 120. Okay? Is the number of starbursts increasing by the same amount every time? Well, if you look at this, okay, if we go here, they increase by 5. They increase here by 7. They increase here by 9. And they increase here by 11. Okay? So, no. They are increasing by an increasing amount. Okay. So can the number of starbursts in each figure be described as an arithmetic sequence? Well, we know that for it to be arithmetic, it has to grow by the same amount. So no, it can't be arithmetic because we don't have a constant rate of change. No constant rate of change. Can it be exponential? And the answer to that is also no, because we're not multiplying. If you look at these numbers, to go from 5 to 7, we would have to multiply 5 by 7/5. I'm sorry, to go from 3 to 8, you would have to multiply 3 by 8/3. And then to go from 15 from 8, you'd have to multiply 8 by 15/8. And we're not multiplying by the same number. So no, it can't be arithmetic and not multiplying by same number. So not exponential, no common rate of change. Or I'm sorry, no common multiply. You don't multiply by a constant rate number. So let f of n be the number of starbursts in the nth figure. Can you write an equation for f of n? So f of n could be, well, let's see. F of n, if you look at this, 1 times 3, so if figure number is n, isn't 1 times 3 just n times n plus 2? So at 10, it would be 10 times 12. Yeah, so that seems to work. All right, so this will give us for any of the figures. So if you want the 100th figure, it would be 100 times 102, which would be a pretty good sized number. We could distribute the n and come up with a different equation. That's pretty straightforward. F of n would equal n times n is n squared plus 2n. That's another way of writing the same equation. And lastly, we could, and this will make more sense once you get into multiplying binomials, but it's the same thing as saying n plus 1 squared minus 1. All right? Again, if this last one you don't quite see, you should see this one, right? Boom, boom gives you that. But to go from here to there, you'll see how to do that later. But it does work out to be n plus 1 squared minus 1. Okay. Here are the quick notes or the Important pieces of information. Sequences with quadratic growth have a constant second difference, which means I need to go back and show you something, which I did not. If you look at these numbers right here, notice this is the first difference. And if we go one more, and we go 7 minus 5, that's 2. 9 minus 7, that's 2. 11 minus 9, that's 2. That's the second difference. All right? So you see this is the second difference. Why is it called the second difference? Is because the second difference is the differences of the first difference. Okay? And so a quadratic growth have a constant second difference. Rules for quadratic patterns have an x squared, something you should see. You get x squared. From right here, you get x squared. That makes it quadratic. Okay? So, second power equals quadratic. Okay? And even this one, even though I didn't show you how this works, you will see it. That's to the second power, so that is also quadratic. So rules for quadratic patterns have an x squared term in them, or can be written as a product of linear factors. Notice, right here, these are linear. N times n plus 2. The product of linear factors makes it quadratic. Now, arithmetic has a common difference versus geometric, which has a common ratio, versus quadratic, which has a common second difference. That's the difference. That's how, and quite honestly, this can keep going. If you want to know what a cubic, which is to the third power, it would have a common third difference. And for something raised to the fourth power would be a constant fourth difference. So this difference idea helps out later on when you're trying to figure out what kind of function you can use to model the data. Okay? Is it linear? Is it quadratic? Is it cubic? And so forth. All right? And that's it for the lesson. Next up will be the check your understanding.